All right. Thank you very much, Mark. And thanks all of you, Tufik, for the invitation. It's fun to be here. Thanks for those of us in the far west, in the early time zones, if you're attending. Yeah, so I was going to tell you about some work that is joint with Marcelo Aguiar and Sarah Bronner, and yeah, that connects things that we like, enumerative things from permutations, descent sets, peak sets, and also the topology of these things called configuration spaces. And here is my plan is that I was going to start by just reminding you what are descent sets and descent numbers and peak sets and peak numbers for permutations and how they give rise to some interesting algebras that sit inside of the group algebra for the symmetric group. And these are all kind of old stories, but some parts of it, particularly having to do with these peak subalgebras, are maybe not quite as well known, how it all fits together. And so I think it's a good thing for us to learn about the first time or review if you've seen it before. And then I'll continue to tell you a somewhat old story having to do with inside of some of these surprising subalgebras, there are families of orthogonal idempotents, and I'll explain, what that means again. But whenever you have families of orthogonal idempotents inside of a group algebra, they decompose the group algebra into representations. And it turns out it's kind of been known for a long time, but again, it's a little bit hidden in the literature that those representations of the symmetric group or the signed permutation groups have to do with the topology of configuration spaces. But what's new in this story is that also the subalgebras defined by peaks have idempotents that are connected to the topology of configuration spaces. So that's the new part, is I'll tell you about how these peak subalgebras and their idempotents connect with topology. And then at the end, if we have time, I'll talk a little bit about some proof ideas. And one of the proof ideas leads to an interesting corollary about higher Lie representations. And that's the plan. So please stop me at any point if there are questions. Also, this talk, if you wanted to follow along, the PDF of the slides is, if you go to my webpage, Google my name, go to talks, I think it's the top talk listed there. So you could be following along. Okay. So let's start by just reviewing descent sets and peak sets for permutations. When I have a permutation, I'm going to call it W in the symmetric group Sn. So that's the symmetric group permuting the letters 1 through n, which I'll abbreviate as the set bracket n. And I'll use a two-line notation usually for such a permutation. 1 goes to W1, 2 goes to W2, n goes to Wn. The descent set is a very classically studied thing, and that is just asking which subscripts I from 1 through n minus 1 do you have a descent from position I to position I plus 1? And is somebody else watching the chat just in case? Oh, the slides aren't advancing. Uh-oh. It says my screen sharing is paused.
I'm not too sure what to do from here. Did you make it full screen to begin with, or is it to scroll
It
down?
is full screen. Let me start over there. Let me stop. I'm gonna just leave the slides for the moment. I'm gonna stop the share. I'm gonna pull it up as full screen first. By the way, thanks folks in the chat for pointing it out. Okay. I'm gonna start share. Okay. All right. When I make it full screen there, now it says, now they'll advance. Are you seeing it as full screen?
We're not seeing it as full screen because we can see everything on the left and right, the tabs, but it's forwarding. I mean, we can see one now, so
Well, shall we go with that?
It looks good to me.
Okay, we'll go with that. Good. Thanks for letting me know. All right. So the descent set is just keeping track of the positions, I, such that Wi is bigger than Wi plus 1. So the values go down as you proceed from position I to I plus 1. And the descent number with a little d rather than a capital D is just the number of descents. Whereas the peak set is looking at the positions I that could be from 1 to n minus 1, such that in the three positions I minus 1, I, and I plus 1, you go up, then down. So Wi is a peak, and on either side, the Wi minus 1 and the Wi plus 1 are smaller values. But in order to make this well-defined when I equals 1, we need to say, what's our convention for position 0? What's the value W0? And we set that to be 0 so that it's smaller than the other values. That means you always begin with an ascent in some sense if you're thinking about the peak set. And then the peak number with a little p rather than a capital P is just the cardinality of the peak set. Okay, so here's an example. If I have W in S7, that in one line notation would be 5173642, you put in where you have descents from 5 to 1, 7 to 3, 6 to 4, and 4 to 2. Those are in positions 1, 3, 5, and 6. So the descent set is 1, 3, 5, 6. And I've indicated with these purple going down edges in the graph of the permutation. Whereas the peak set, I should put in this new point in the graph, which is W0 equals 0, and then look where I see peaks, where you go up and then down. So these orange circled positions are where you have peaks, right? 1, 3, and 5. So the peak set is 1, 3, 5, and the peak number is 3. And here's an example where we do all 6 permutations in S3. We write down their descent sets that could be any subset of the numbers 1 through n minus 1. So it's the numbers 1 to 2. And their descent numbers are here. And then if we look at the peak sets, on the other hand, notice that you can have empty peak set, or you could have the singleton 2 as your peak set, or you could have the singleton 1. But you can't have 1, 2. You can't have a peak in 2 adjacent positions. And so this means that the peak numbers can only be 0 or 1 in this case, because n equals 3. And also notice that two things that have the same descent set, for example, this permutation and this permutation, they also have the same peak set. So if you tell me the descent set for the permutation, you're telling me where all of the ascents and descents are in various positions. You're also going to be able to predict where are the peaks. So let's point that out. Note that descent set definitely determines the peak set. You can read it off. The peak set is the positions I that are in the descent set, but they're not preceded by a descent. They're preceded by an ascent. And the peak set, as we said, is what's sometimes called a sparse subset of the numbers 1 through n minus 1. That means if I is a position in the peak set, then it can't be followed by another position in the peak set. You can't have 2 peaks in a row. So for example, if we had a permutation in S4, the potential peak sets are empty, or the singleton 1, the singleton 2, the singleton 3, or the singleton 1, 3, which doesn't contain 2 adjacent values. But you can't have 1, 2, or 2, 3, or 1, 2, 3 appearing as peak sets. So there's only 5 possible peak sets there. And if you think about this, that implies that the number of peaks, could be, it's between 0 and at most something like n over 2. And if I got it correctly, then it's n minus 1 over 2 ceiling is the maximum number of peaks. And also, if you think about these sparse subsets of the numbers 1 through n minus 1 that don't contain 2 adjacent values, it satisfies a Fibonacci recurrence for their cardinality. And so I think there are exactly fn plus 1, that Fibonacci number, many possible peak sets, where our convention for the Fibonacci numbers, they satisfy the usual recurrence, starting with f0 is 0 and f1 is 1. For example, there were 5 possible when n equals 4, and that 5 is the Fibonacci number, actually f4 plus 1. It's f5. Okay. Any questions so far? Just checking. Good. So let's now move on to these algebras, these surprising subalgebras of the symmetric group algebra that come from descents and peaks. So we need to first start with this ambient, this big algebra, which is the group algebra for the symmetric group. I'm going to use rational numbers as my coefficients in front of permutations. We could be working sometimes in some of the results with more general coefficients, sometimes the integers, sometimes fields whose characteristic is not 2, but let's not worry about the more general statements. And the group algebra is just formal linear combinations with rational coefficients in front of each permutation W. I think of it as each permutation W is now a basis element in a vector space over Q with n factorial basis elements indexed by permutations. And they each have a coefficient that's a rational number in front, C sub W. And you add them coefficient-wise, so the addition just adds coefficients. And you multiply them you Q linearly extend the group multiplication. So the basis element U times the basis element V gives you the basis element UV, whatever permutation UV is, and you carry along the coefficients Q linearly. So I wrote out formally what the multiplication would be. And it's an important algebra. We know that it comes up all the time in representation theory, and in particular, now we're talking about representations of the symmetric group where it would be relevant. Okay, so inside of this group algebra, here are some theorems. There are a whole bunch of subalgebras that are a bit surprising that they exist. So I'll tell you in a moment who proved these things, but let's just put the statements all on the page. Inside the group algebra, where these coefficients CW can be arbitrary rational coefficients, you have the descent algebra. It's sometimes called Solomon's descent algebra, and I'm going to call it Sol of Sn. Okay, I'm sorry, but somehow all of these algebras, there are no standard names in the literature. Different people use different names for these algebras, and I just picked one. And so what is this Solomon descent algebra for Sn? You just take the Q-linear subspace of the group algebra where the coefficients CW only depend upon the descent set of W. So it means when you look at two permutations in the same descent set, they should have the same coefficient. Okay. And all of the rest of these subalgebras are defined similarly. Inside the descent algebra, you find this thing called the peak algebra or the peak subalgebra. I'm calling it capital P sub n, where the coefficient CW only depends upon the peak set of W. Okay. A priori, that sounds like a Q-linear subspace because we're imposing some equations on the coefficients that they're constant along peak classes. But it actually turns out to not just be under addition and scaling, a subspace, it's actually a subalgebra. It's closed under multiplication. And then within the descent algebra, there is this thing called the Eulerian subalgebra. I'm using calligraphic E of Sn as the notation, where the coefficients depend only on the descent number. So this is a subspace of the descent algebra where the coefficients depend upon the descent set. And then inside the peak subalgebra, there is what's sometimes called, nobody calls it the peak Eulerian subalgebra necessarily. I think I made that up, but I need a name for it. The peak Eulerian subalgebra is, I'm calling calligraphic P sub n, where the coefficients only depend upon the peak number. Okay. And there's a reason why these are called Eulerian. This is called the Eulerian subalgebra. Let me not get into it. I wish that its dimension was the Eulerian number, but that's not true. That's unfortunately not why it's called the Eulerian subalgebra. Okay, so and who observed these things and proved them were, as I said, Solomon in 1976 would have, I think been the person who observed the existence of this descent subalgebra of the group algebra. And he proved something a little more that I'll get into in a moment. And the fact that inside of the descent algebra for Sn, there's this Eulerian subalgebra, this actually came from two independent sources. So it turns out that Gerstenhaber and Schack in 1987 were actually looking at this thing called Hochschild homology of algebras. And they came up with certain idempotents that had appeared earlier in work of Barr on Hochschild homology. And somehow they ended up writing down orthogonal idempotents for this Eulerian subalgebra because it was decomposing Hochschild homology in a certain way. They called it the Hodge decomposition for Hochschild homology. So they had a reason to care about this Eulerian subalgebra and define it. But also Garcia and Reutenauer, in their work on free Lie algebras in 1989, they ended up, also observing these Eulerian idempotents and this Eulerian subalgebra. And so, just independently, they had reasons to care about its existence. On the other hand, the peak story. So first it was Catherine Nyman in her thesis who observed something. She didn't quite have the peak algebra. She had a large ideal inside of the peak algebra, a non-unital subalgebra of it. But she had something pretty close to the peak algebra that she had observed was closed under multiplication. And then in work that she did jointly with Marcel Aguiar, and this is Nantel Bergeron, not Francois, in 2004, they defined the whole peak algebra, and they observed that there's also this peak Eulerian subalgebra where you group further according to just the number of peaks rather than the peak set. Okay, so that's a bit of the history on it. By the way, any questions so far? Let me not go too fast. Okay. And here's just some examples to, it's kind of fun to play with these things a little bit. There is some surprise here. And when I want to, for example, check that some of these things are subalgebras or how the multiplication goes, what I usually find it easier for working in the group algebra is not to use two-line notation for my permutations, but actually to write my permutations as products of adjacent transpositions. So little s sub I is the permutation that swaps I and I plus 1. These are the Coxeter generators for the symmetric group. And so here's the identity is just the element 1. That's also going to be the unit, the 1 in the group algebra. This is the adjacent transposition S2, S1. This one is S1, S2 is the 3 cycle in the S3. S2, S1 is another 3 cycle. And the longest element, I've written down shortest expressions for all of the permutations in the Coxeter generators. The one that has the longest expression is of length 3, and it has 2 such expressions, S2, S1, S2, and S1, S2, S1. Sometimes it's called W0, that longest permutation. It's the reversing permutation. And, here were the descent sets, and here were their descent numbers. So what would be the Solomon algebra for S3? It would be the span inside of the group algebra of these elements indexed by the potential descent sets, the empty descent set, singleton set 1, singleton set 2, singleton set, the set 1, 2. So Y sub a set J is you sum over all the permutations whose descent set is exactly J, and they should be a Q basis for this Solomon descent algebra. And so like in this case, Y empty is just the element 1, Y sub singleton set 1 is S1 plus S2 S1, Y sub 2 is S2 plus S1 S2, and Y sub the set 1, 2 is just the longest element. And you can start multiplying these out. For example, this element, Y sub singleton set 1, when we square it, we write down 2 copies of what that sum is. We multiply out those parentheses. We get S1 squared, S plus S1 S2 S1 plus S2 S1 squared plus S2 S1 S2 S1. And then you have to start using these relations among the adjacent transpositions, which are, what you might call Coxeter relations. Like S1 squared is just the identity. And we don't see any of these Coxeter relations, the fact that SI and SJ commute if the I and J are far enough apart, if they're at least 2 apart. But you will need to use some of these relations, like here, S2, S1, S2, S1 is the same as S1, S2, S1. And that's, a Coxeter relation, a braid relation. SI, SI plus 1, SI is SI plus 1, SI, SI plus 1. And these are like very important in this kind of descent theory of symmetric groups. And so you realize, 1 is Y empty, W naught is the Y for the full set 1, 2, and S2 plus S1, S2, that's Y sub the set singleton set 2. So this thing did expand as back inside this subspace, which is Solomon's descent algebra. And it's a bit surprising. And if one is really patient, one can write out some more multiplications of these y sub j's. So I've written out all the possible multiplications of y sub j's, expanded them back as a sum of y sub j's. And you could check that some of these other subspaces, like the Eulerian subalgebra, is closed under multiplication. For example, y1 plus y2, that is the sum of all the permutations with exactly one descent. That's one of the basis elements for the Eulerian subalgebra inside S3. It's got things with 0 descents, things with 1 descent, and things with 2 descents. Those sums are its basis. And for example, this thing squares. If I compute the square, I could use these relations over here to compute the square, and it's 4 times the things with 0 descents, plus 4 times the things with 2 descents, plus 2 times the things with 1 descent. So it's back in the Eulerian subalgebra. And I'm not going to check, the rest, any more of these. That would be presuming too much of your patience. But let me point out that these various algebras, what are their dimensions, based on what we've been talking about? Like the group algebra, right, has basis elements indexed by permutations. So its dimension should be n factorial. And this is the case of S3. So it's 3 factorial, 6-dimensional. The descent subalgebra should have 2 to the n minus 1 as its dimension, because that's how many possible descent sets there are. They're the subsets of n minus 1. The peak subalgebra, we said that the peak sets were these sparse subsets, and there's Fibonacci many, so it should have a Fibonacci number dimension, which in this case was 3. The Eulerian subalgebra, right, the number of possible descents you can have is 0 through n minus 1, so it should be an n-dimensional algebra. And this peak Eulerian subalgebra, right, its dimension should be the different numbers of possible cardinalities of peak sets. What are the values that little peak of W can take? And we said that went from 0 up to n minus 1 over 2 ceiling. So that should be of dimension n plus 1 over 2 ceiling. Everybody okay so far? Questions? Okay.
Okay,
So,
I have a quick question. This
yeah,
is
Doran.
cool. Are there other permutation statistics that have the same phenomena, like the major index, number of inversions, and kind of the descent is just you can do generalized patterns. So this phenomenon also holds for other.
Yeah, I'm not actually sure what you mean by other generalized patterns, Doran. As far as like major index and inv, I don't think so. That we can just take, the sums over constant maj or the sums over constant inv and get a subalgebra.
Thank you.
But generalized patterns, I'm not sure what you mean.
Yeah, but in this case, descent, so like the up, down, up, for example, number of pattern up, down, up, up.
Oh, I see what you're saying. Like peaks is a kind of a descent pattern. Oh, that's a great question, and I offhand don't know the answer. But
okay, thank you. It's
yeah,
very beautiful construction. Thank you.
thank you. Good. So yeah. Okay. So what did Solomon actually prove? I'm not just mentioning this for the fun of it. This will be relevant because we need to not only talk about permutations, but signed permutations will play a role here. So what Solomon in 1976 actually observed and proved is that if you start with any finite real reflection group W, and I'll explain, and on that second half of the slide here, you'll see that the symmetric group actually is one of these objects. There is a good notion of descent set, and descent algebra is what he observed. So the descent set comes from thinking about a finite real reflection groups always has these generators like the SIs that play the role of the adjacent transpositions. They're called Coxeter generators. And what's a finite real reflection group? It's a subgroup of the general linear group over the reals acting on your Euclidean space that's generated by reflections, where you have hyperplanes and you fix the hyperplane and reflect in the hyperplane. So it turns out when you take all of the reflecting hyperplanes in the space, and here's a picture what happens with S3, breaks up the space into these connected components called chambers. You pick your favorite chamber, you look at the walls of that chamber, those are a subset of the hyperplanes, and you just take the reflections in those walls, they give you a very nice generating set, what's called a Coxeter generating set for your finite real reflection group. And so here I've drawn this for the symmetric group Sn. You think of Sn, and this is what's called type A, the type A reflection group. It permutes the coordinates in Rn, but let's cut down the dimension by 1 just to make it easier to draw the pictures. And in the hyperplane where the sum of the coordinates is 0, it also sends that space back to itself, which is drawn here for n equals 3. This is supposed to be the plane inside of R3 where the sum of the coordinates is 0. So it's acting by reflection. So the SIs, for example, S1 is actually the reflection through the hyperplane where the coordinates x1 and x2 are equal. And the adjacent transposition S2 is the reflection through the hyperplane where the 2 and 3 coordinates are equal, x2 equals x3. So this is an example of Coxeter generators for a real reflection group, our adjacent transpositions. And you define the descent set as for an element in a finite real reflection group. The descent set, des of W, is the subset of the Coxeter generators such that when you multiply on the right, it decreases your length with respect to the Coxeter generating set. That decreases the number of those S generators needed to write the expression for that element. So this is not something that Solomon had developed. That Coxeter theory existed and the descent set existed. But what he observed is that if you look inside of the group algebra for your finite real reflection group at those elements whose coefficients only depend on the descent set, again, that Q-linear subspace actually is a subalgebra. Surprising. And we actually are going to need another example of this, which is the sign permutation matrices. So I'm calling it Sn plus or minus. This is the hyperoctahedral group. You could think of it as all n by n signed permutation matrices, where there's mostly zeros in your matrix, but every row and every column has exactly one non-zero entry, which is a plus or minus 1. So a sign is allowed. This is called the type B or type C real reflection group, and it acts on Rn by permuting coordinates and allowing you to negate coordinates. So it turns out when you do this Coxeter construction to get a nice set of Coxeter generators, you look at how it acts on the space. I'm pointing at the picture for n equals 2. You pick one of these chambers. This chamber would be like where the coordinates, this looks like where x2 is bigger than x1 is bigger than 0 in terms of the coordinates on the space. And you look at its walls, and its walls are going to give you reflections that give you Coxeter generators. And in general, one of those reflections will be called S0, and it negates the first coordinate, the x1 equals 0, the x1 coordinate. That's a reflection through the hyperplane x1 equals 0. And the other generators are, again, the adjacent transpositions S1 through Sn minus 1 that reflect in the hyperplanes xi equals xi plus 1. And this gives you a notion of descent set for signed permutation matrices. Now you can have a descent in position 0. So there's I goes from 0 to n minus 1 when you're looking for these descents. And it still can be described in the same way as it's the positions I where wi is bigger than wi plus 1. But again, you have to artificially set w0 to 0 and then use the usual integer ordering on negative numbers and positive numbers. So that's the Coxeter descent set in type B for the sign permutations. Okay. And why is this important for us? Well, there's two things that are actually really important and very illuminating. So this is a part of the story that some people know. And to be honest with you, I had heard about these things years ago, and I hadn't really appreciated it until we started working on this project. So first of all, there's an observation, a theorem of François and Nantel Bergeron from 1992 that Okay, inside the group algebra for the sign permutations, so that's the type B group algebra, Solomon already pointed out that there's a type B descent algebra where the coefficients depend only upon this descent set of type B. But then there's a type B Eulerian subalgebra that I'm calling calligraphic E of the hyperoctahedral group, Sn plus or minus. And again, it's just you take the elements in the group algebra whose coefficients depend only on the number of type D descents, the descent number. Interesting. And they actually wrote down some orthogonal idempotents that we will get to. And here's another really interesting thing is much later, 2004, Marcela Aguiar and Nantel Bergeron and Catherine Nyman in that same paper where they started looking at the peak subalgebra, they showed how the type B Solomon algebra relates to the peak subalgebra and kind of in a certain way explained why it exists. And the same with the Eulerian part. So what's the story? When you have type B permutations, the signed permutations, there's an obvious group homomorphism to ordinary permutations by forgetting the signs, okay? Sn is a quotient of Sn plus or minus, where you mod out by the subgroup of all sign changes. And this is a quotient group homomorphism. But then any group homomorphism like that, it leads to an algebra homomorphism, a surjective algebra homomorphism between the type B and type A group algebras. When you look at the type B Solomon algebra, under that same homomorphism where you just forget the signs in the sign permutations, that's all you do. You erase the minus signs. You do land inside the type A Solomon algebra, but what you hit is actually the peak subalgebra of the Solomon algebra. So this is very, very interesting. In some sense, maybe this is the raison d'etre for the peak subalgebra, is because type B descent algebra maps into type A, but it doesn't hit everybody in the descent algebra. It hits the peak subalgebra. It's the image subalgebra. And then, same story here. If you look at this Eulerian, the type B Eulerian subalgebra that the Bergerons had introduced inside of the type B descent algebra, its image is exactly that thing that we were talking about earlier, the peak Eulerian subalgebra of type A, where you have the constant coefficients when you have the same peak number. So maybe that's the real reason why that should exist. Okay, so that's a bit of history and philosophy that I've started to appreciate a little bit more, and I wanted to share with you. Questions? Good. So let's talk about some items.
The type B peak subalgebra is an image of some another algebra. So you explained the type A peak subalgebra, but not the type B peak subalgebra.
Yeah, and you know what, Yuval? You would have to define for me the type B peak subalgebra. What is the type B peak subalgebra? You'd have to remind me what a type B peak is. I'm sorry, I've forgotten.
Okay.
But thanks for bringing it up. Then no, this is a good point. Yeah, I don't know. That is a good question. Okay. So let's get to some idempotence, some topology, and then something new having to do with peaks. So again, there's still like a known part to this story that's kind of interesting, but it's a little bit hard to find it in the literature. So if we look at those Eulerian subalgebras, constant number of descents, constant number of peaks, and constant number of type B descents, all three of them actually have the most simple possible structure as rings. They are actually commutative rings. Descent algebras are not commutative, but these subalgebras are commutative and they're semi-simple. And what that means is, another way of saying commutative semi-simple is, as rings, they're just a direct product of copies of the field Q, just with component-wise multiplication, component-wise addition. What that means is, you can actually find basis elements in each coordinate. You can find explicit Q bases of primitive orthogonal idempotents, E sub I, And what does that mean? It means the EI squareds are themselves, EI squared is EI. They commute with each other. EI, EJ is equal to 0 is EJ, EI. So they commute and annihilate each other. And the one, the unit from the ring, is the sum of all these idempotents. So what should these EIs be? They should be the basis elements, where you have put a 0 in most of these Q positions and you put a 1 in one position. That's what these EIs are playing the role of. Okay, so you can write down these magical bases, these primitive idempotent bases explicitly for the type A, the symmetric group Eulerian subalgebra. So Gerstenhaber and Schoch, this is exactly what they were interested in because these idempotents decompose their Hochschild homology. And Garcia and Reutenauer were also interested in these idempotents because they came up naturally in their study of the free Lie algebra. So they wrote these things down. I'm not going to write down the formulas, but they're nice formulas that have to do with generating functions involving descents of permutations. But let me skip the formulas. And then in type B, that Eulerian subalgebra that Francois and Nantel Bergeron had found, similarly, they were able to write down explicit orthogonal idempotents, again, having to do with type B descent numbers. I'm going to suppress the formulas. And then in these peak subalgebras, as far as we know, people hadn't been writing down these explicit orthogonal idempotents. But if you take the orthogonal idempotents of type B in this Eulerian subalgebra for type B, forget the signs, apply this pi map that just forgets the signs, they should again obey the equations. The images should still satisfy, EI squared is EI. They should commute with each other. One should be their sum. The only thing that's funny about this is some of these images should be 0. Remember, here we've got n different idempotents. When we forget the signs and take their images, we're mapping into an algebra which we know has dimension n plus 1 over 2 ceiling. So about half of these should vanish. And I'm going to tell you later which ones vanish exactly. So the topology actually, told us exactly, oh, I see, these are the ones that should vanish. So we will get there. Okay, so we have these idempotents inside these Eulerian type subalgebras. They're pretty explicit. And whenever you have a family of orthogonal idempotents, EI, inside a group algebra or any finite dimensional algebra, it will give you a decomposition of what you might call the left regular representation for that algebra. So the group algebra, we think about our reflection group W, whether it's permutations or sign permutations, multiplying on the left the permutation or sign permutation basis elements, that's the regular representation. If we take the group algebra times one of these idempotents on the right, it still has a left multiplication action of the group. And so we get these representations generated by these idempotents inside the group algebra. And it decomposes the group algebra because of they were these orthogonal idempotents. That decomposition, it turns out, for the Eulerian idempotents of type A and for the peak algebra and for the Eulerian idempotents of type E, they're all going to connect to cohomology of certain spaces. And these spaces are going to be the cohomology rings of what are called configuration spaces, ordered configuration spaces. So what are those? First of all, I'm always going to be taking cohomology with Q coefficients because we were using the Q coefficient group algebra. And the ordered configuration space conf n of space X is you just look at sequences of points in your space X that are unequal to each other, but have been labeled point number 1, point number 2, up to point number n, and they can't collide with each other. You just look at the space of all such ordered configurations of n distinct points. And it has a topology inside of the product topology on your space X to the n. Okay, so here are the theorems that are classically known. Although, again, it's like you have to ask experts to find out these theorems. So from work of Phil Hanlon around 1990, where he was computing the SN representations on the space generated by Eulerian idempotents, if you combine that with work of Sheila Sundaram and Volkmar Welker on topology of configuration spaces and hyperplane arrangement complements and subspace arrangement complements, their work from 1997 with equivariant Goreski-McPherson formulas. You put the two together, you ask Sheila Sundaram, and she will tell you that the configuration space of n distinct ordered points in R3, so like in three-dimensional space where we live, that configuration space of n points, its cohomology as a total cohomology, it's like cohomology is a graded thing. It has a cohomological grading, but the total representation is going to be the group algebra, the regular representation. And when you look at where the cohomology lives, because these are points in R3, that cohomology only exists in even dimensions. You're going to have H2K, or where you have non-zero cohomology, and the H2K cohomology as a symmetric group representation, it carries this Eulerian idempotent generated representation. So you have to take the Eulerian idempotent for Sn indexed by n-1 minus k. There's somehow a reversing of the indices when you look at the cohomological grading in this space versus which idempotent generates the representation. Very interesting. And then there's a type B story like this. So Sarah Bronner in 2022 had examined some kind of a type B analog of this ordered configuration space. I'm going to call it Y sub n. It's what's called the Z2 orbit configuration space for not all of R3, but you puncture R3. You don't allow points to be at the origin, and you consider the antipodal map or the negation map, which sends points in R3 to their negatives. Consider that Z2 action, and you look at ordered configurations of points that are non-zero in R3, so not at the origin, such that none of these points are equal to each other and none of them are equal to their negatives. None is sent to each other by negation. So no xi is not allowed to equal to plus or minus xj. And that thing carries an action not only of the symmetric group permuting the coordinates, but also the signed permutations act on it. You think of the sign change in the ith coordinate sends one of these points to its negative. If you think about that, the entire hyperoctahedral group of all sign permutations will act on this Z2 orbit configuration space. And its topology, its cohomology ring, is going to give you the group algebra or the regular representation for the sign permutations. And it only has cohomology in even dimensions, 2K. And in the 2K cohomology, the representation of the hyperoctahedral group or sign permutations is exactly the one generated by the n-kth type B Eulerian idempotent. Okay. So we were aware of this. In particular, Sarah was aware of this. She talked about this at Cornell. She talked to Marcello, who knows the story for peaks. Oh, sorry. This is a remark for experts. I'm going to skip it. Experts, take a look at this slide because Sarah was really doing something slightly more general. But the point is that Sarah was talking about these results, and Marcello said, maybe we should start looking at this. And so here's the theorem that came out of a great question that Marcello asked Sarah. Is there a space that interprets those peak idempotent representations of the symmetric group? And yes, there is. So the way you get it is you take that type B orbit configuration space. That was the space we called Yn. Remember, we said it has not only permutations, but also the sign changes. Just take the subgroup of sign changes in each coordinate, independently in each coordinate. You take those points that were not equal to their negatives and you negate them. Look at the quotient space. So on the one hand, it's the quotient of this orbit configuration space. On the other hand, it itself is the configuration of n-ordered points in this space where you just take R3 minus 0 and you mod out by the antipodal action. You mod out by negation. That space that I'm calling U is, you could think about it as being like RP2 cross 0 to infinity. Now the question is, which line are the points on and how far away from the origin? That gives you two coordinates. Or if you like, it's RP2 cross R. So this quotient space that we're calling Zn, it's the configuration of n ordered points in RP2 cross R, that topological space. And what we're able to show is, okay, its total cohomology is again a copy of the regular representation of Sn, and its cohomology is only potentially going to live in even dimensions, and the 2kth cohomology is this representation of Sn generated by the n minus kth peak idempotent. But remember, we said that some of these things should vanish, half of them should vanish. In fact, this cohomology doesn't just live in even dimensions, it vanishes unless the n minus k is also even. So it roughly lives in every fourth dimension. Here's again, you have H0, H4, H8 are the only cohomologies that will survive. I'm just going to leave that up for a moment, and if there are any questions. Okay, so what about this there? So remember, the idea is we had descents and descent number. These idempotents, had to do with the cohomology of Xn, this configuration space. Type B descents and the type B Eulerian idempotents had to do with this orbits configuration space, this Yn's, its cohomology. And now we're saying the Zn, this quotient, which is the configurations of points in this space, has to do with the peak idempotent cohomology. Excuse me, has to do with the peak idempotent Sn representations. And so I'm just going to give you a few ideas of the proof and a corollary. So since we were looking at the cohomology of some quotient by a subgroup of our sign permutations acting on the space Yn, the entire sign permutation group acts freely on that space. You have like a covering space situation. We're just taking a subgroup of this group that's acting freely. And so when we want to understand the cohomology of the quotient of that space by this free action, covering space theory says, oh, it's the same as taking the cohomology of the space before you quotient and just looking at the invariant subalgebra. So we have to understand this ring and take its invariant elements under the group action for whatever group that we quotiented by. In this case, it's the sign changes. The nice thing is those orbit configuration space of the original X sub n cohomology, that orbit configuration space cohomology, they have really, really nice presentations. These are very concrete rings. I didn't write down the presentations for you, but they have very, very explicit presentations that essentially come from work originally of Varchenko and Gelfand on the ring of Heaviside functions in '87. Then you have to take you look at the associated graded ring of the ring of Heaviside functions. But then also work of Mark de Longueville and Karsten Schultz wrote down these presentations. And actually, I have omitted someone else who looked at similar presentations. Hikoten Kadel, who was a student of Fred Cohen, actually had worked on something that a presentation that looks equivalent. And then work of Mosley, who was a student of Nick Proudfoot in 2017, came back and rederived these presentations in an insightful way. So we've got concrete presentations for these rings. We just have to take to the Z2 to the n invariants, and it's doable. The first thing you do is you diagonalize the action. This is a commutative group. You can simultaneously diagonalize a basis. It's all very nice. So that's helpful. A second really helpful idea here is when you're working with signed permutations and you look at the hyperplanes, the reflecting hyperplanes for that reflection group, there are two kinds of hyperplanes. There are the ones that look like xi equals plus or minus xj, and there are ones that look like coordinate hyperplanes, xi equals 0. There are these two orbits of hyperplanes under the hyperoctahedral group, under the sign permutations. The orange ones are the xi equals 0 in this picture. The purple ones are the xi equals plus or minus xj. And it's the hyperplanes that give you the generating variables in the presentation that I didn't tell you. So you write down the presentation, there's one variable for each hyperplane. The fact that there's two orbits of hyperplanes actually gives you a really nice filtration, and which leads to a bi-grading on those rings. So it's not just cohomologically graded. There's actually an extra grading running around having to do with how many of these hyperplanes variables you use versus how many of these variables you use. That bigrading on this ring is actually inherited by this invariant subring that we were trying to study, the cohomology of Zn. And so having a bigrading is really helpful. In particular, it leads to this corollary, which surprised us. So there's a well-known way to decompose further the cohomology of that type A configuration space. You take this kth Eulerian idempotent, or the n minus kth Eulerian idempotent, which is the 2k cohomology, and you can decompose it further according to partitions of n that have n minus k parts. And each one of those has a well-known W representation, SN representation called Lie sub lambda, the higher Lie character of Thrall associated with lambda. So Yuval is an expert on these higher Lie characters. And if you group those higher Lie characters according to essentially their number of parts, you're further decomposing the type A cohomology. Well, in our bigraded decomposition, I just said that there was a bigrading on this cohomology of the Zn, and this is again supposed to be the symmetric group algebra. The bigraded thing decomposes according to not just number of parts, the Lie lambdas, the number of parts in lambda, but how many of the parts are odd versus even parts. So in our bigrading, naturally, you get the sum of Lie lambda as representations for the lambdas with n minus L parts, exactly n minus k of them, which are odd-sized parts. Anyway, so that's the end of my story. I want to thank the conference and Tufik and Mark, and thank you all for your attention.